curves, or Stoke's theorem, states that the total amount of the vector field F rotating along the loop or the curve C, which is represented by the closed line integral of the vector field F over dr, is equal to the total curves of the vector field F around each point of the surface S bounded by C, which is represented by the double surface integral over ds. And now, let's have the first part of the equation. The smooth vector field F having components x, y, and z is in R3. And C is a loop, curve, or closed line, whatever, which bounds the surface S. dr is an infinitely small element of the curve C. Its length is the magnitude of the vector dr. We also have a scalar product between the smooth vector field F and the vector dr. Knowing that the vector field F can be represented by F1, which is a collinear vector to dr, and by F2, which is an orthogonal vector to dr. By orthogonality, the scalar product will be equal to the vector F1 multiplied by the vector dr. Lastly, the scalar product is summed up by the line integral over an infinitesimal element of that line. This line integral measures how much the vector field F is flowing along the boundary curve C. And now let's jump for the second part of the equation, the double surface integral. The surface S is not a closed surface. It is bounded by the curve C. ds is an infinitesimal element of that surface. Vector ds is an orthogonal vector of ds for the surface S. Take into consideration that there is a cross product between the nabla operator and the vector field F. Keep in mind that the nabla operator is a vector whose components are partial derivatives. This cross product will result with a curved vector field, measuring the amount of the vector field F rotating around a point of the surface S. One more important step you have to bear in mind. The curved vector field undergoes a scalar product. Similarly, the curved vector field is made up of the curved vector field 1, which is a parallel vector for the vector ds, and it also is made up of curved vector 2, which is an orthogonal vector for the vector ds. Upon orthogonality, the result will be the product between the vector ds and the curved vector field 1. Lastly, the scalar product for each curved vector of each ds is summed up by the double surface integral. This surface integral measures the local curve, or the rotation of the vector field F with ds of the surface S. Because of the opposite rotations in ds of vectors of equal magnitudes, all of the vector fields F cancel each other, leaving a result of vector fields along the edge of C. Taking all that into consideration, the sum of the vector fields F rotating along the curve C is equal to the sum of the vector fields F rotating at each point of ds within the surface S. This is what this equation states. All this information are extracted from my book Tensor Calculus in the Theory of Relativity.